Do you know that Tesla Autopilot utilizes a camera for sign understanding? It tracks the traffic lights on the road. Whenever traffic light shows the red, it slows down and waits until the green light. It's capable of giving way to pedestrians even. One of the main components that provide this decision-making are cameras. During the presentation, we see how the grouping of different class of objects is performed. I am Alper Kayabaşı. Today I am going to explain the fully convolutional neural network for semantic segmentation paper comprehensively. Let us begin. First, I define what semantic segmentation means and why we need such a method. Second, I explain which type of architecture is preferred with the reasons and how added connection handled to segment different scale objects in image. Third, I try to introduce learnable upsampling that Jonathan proposes over bilinear interpolation. Fourth, I elaborate on which kind of loss function is utilized to reach the objective. Fifth, I mention conditional random field that increases the segmentation performance as a post-processing technique. Sixth, I give qualitative and quantitative result of tried methods. At last, I summarize the key point and give my deductions that relate deep learning with conventional computer vision. Semantic segmentation aims to perform pixel-level labeling with set of object categories for all image pixels. Many application areas utilize the segmentation. For example, medical people try to measure surface area or volume of brain tumors. Such a detailed analysis can't be performed with object detection type methods. Furthermore, the model extracts a boundary of tumor. All of this information helps radiologists to diagnose the state of patient. Let us imagine that robots wander around farmland to clean wheat. It distinguishes crops from weeds via segmentation also. FCN architecture contains two modifications that removes the restriction on input size and provides a fusion of multi-scale information. As a first, I will mention about convolutionalization. Before FCN, networks include a classifier that is rooted from fully connected layer. A fully connected layer supports a fixed size image since its connections are fixed. We have to resize the input image to supported image size if its size doesn't match with the supported image size. FCM provides a solution so that networks can get varying sizes of image as an input. A fully connected layer flattens the loss feature map before it processes. To convolutionalize the network, all of the connections to each output is reshaped to size before flattening. Each reshaped filter corresponds to one filter of convolutional layer. As a second novelty, skip architecture connects the features from lower layer to higher layer, so that network fuses the information with different receptive field sizes. Briefly, receptive field of neuron defines the area of input that determines the value in the neuron. Therefore, the connection from the lower layer contributes fine and local information, while the higher layer connection includes coarse and global information. The blend of multi-scale information provides a scale invariance capability. Top, middle, and bottom probability map of image in the figure belonging to FCN 32, FCN 16, and FCN 8. Let us mention about upsampling issues. Bilinear upsampling takes a weighted average of 4 points to determine the pixel values between these 4 points, where the weight corresponds to ratio of area across the diagonal and total square-shaped area. They place this upsampling at the last layer of their network. On the other hand, learnable upsampling rescales feature maps that are to be fused. Learnable upsampling is performed with the help of transpose convolution. Transpose convolution multiplies kernel with input, and it shifts this response with displacement of multiplied input from the origin. Therefore, network has a complicated upsampling scheme. I also remove this upsampling to inspect how much benefit it brings. There is a minor performance drop. However, it is worth mentioning transpose convolution-based upsampling, since it was amongst the pioneers of learnable upsampling. FCN utilizes a cross entropy as a loss function. I will explain each term clearly. H, W, and C in the upper index refer to height of each image, width of each image, and total number of classes in dataset. Y sub IC equals 1 if class index is the same as the class of ith image. Otherwise, y equals 0. It is considered as we compute a classification loss on each pixel based on its ground truth annotation. A conditional random field encourages spatially closer pixels to be in same group, and vice versa. However, conditional random field discourages the neighbor pixels belonging to the same group, if high intensity differences occurs between them. After I apply conditional random field, the segmentation mask looks like a hazard starts to appear like a real airplane, as if it was in the original image, since CRF provides consistent labeling that brings sharper boundary and fine details. FCN uses the mean intersection over the union as the accuracy metric in the evaluation. Intersection over union tries to quantify how much prediction overlaps with the ground truth. For a computation, the intersection of ground truth and prediction is divided by all pixels predicted as positive. Mean intersection over union is the average of intersection over union for all classes. Here we see theoretical findings reflects both quantitative and qualitative results. FCN 8 ranks first in terms of mean intersection over union. Following FCN 8, FCN 16 takes the second place, and FCN 32 has the lowest performance. Furthermore, conditional random field brings a positive effect on all architecture, as seen in qualitative analysis. Quantitative results are evaluated on Pascal-Vogt 2012 dataset, which includes 20 classes. Qualitative results are tried on arbitrary images downloaded by Flickr. I see that deep learning-based semantic segmentation empirically outperform conventional techniques such as spectral clustering. However, there are intense inspiration from conventional vision to learning-based vision. Multiscale information fusion with skip architecture is similar to multiscale image representation in Gaussian pyramid. Furthermore, the CRF method invented before is integrated into FCN as a post-processing, which results in better performance than the network without CRF. We see that concept in classical vision transferred into deep learning, and it is continuing to inspire a solution that are integrated into deep learning pipeline. Thank you for your attention.